next, the pronunciation is a little tricky. It's Andrew Stone. Is that it? All right. Andrew, come on up.
I just want to say that you'd be amazed how many people I say my name is Stone and they say, "Can you spell that?" I'm like, it's like rocks and pebbles, and they're like, "So how does that spell?" It literally happens like half the time. Right. So I want to talk about a different extension block system. So basically, Bitcoin has a serious problem, which is how to upgrade the network. Even if you're like a SegWitter or even a large blocker, this problem has been in your face for the last 2 years. So current approaches for upgrading is well, all right, so in order to upgrade, you got to convince people that this code works, right? It's good. So how are you going to do that? Well, you could have a sandbox, like a test net, right? Altcoins, and then of course there's a layer 2 network or a soft hard fork. And I just wanted to indicate there, like, I don't really know quite the audience I'm talking to, but there are people who say that it's unnecessary to upgrade Bitcoin at all. The technology is perfect as it is. So I just put up here a little Radio Shack ad from the 90s. And every single item on that first page is basically obsolete. It's all been upgraded. And so really the promise of Bitcoin beyond gold is that it is a technology that is upgraded, right? And it's a, obviously limited supply. So here are the problems with the current upgrade approaches. The problem with the sandbox is that the use cases are sort of artificial and limited. There's nothing at stake, right? No one can steal money from you, and that means if no one can, hack your code to steal the money, they're not going to try, right? So no black or white hat attention. Also, if you're an obscure, just on testnet, you're a security researcher and you say, I found a bug in testnet, it's not going to make the front pages compared to finding a bug in, Bitcoin's mainnet. The problem with testing your approach in the altcoins, and in 2012, this was a big thing, you should try your stuff in an altcoin. Well, so why don't we ask Vitalik to now, shut off Ethereum, and since, he's proven that it works, right? Okay, so now let's turn that off, and we'll bring it into Bitcoin, right? So the problem with an altcoin is you create a competitor. So then you could argue, well, who cares? Because, I'm not a Bitcoin maximalist, and we can just transfer to, new cryptocurrencies every decade or so. And I'm not an economist, but currency stability, I think, is pretty important in economies. And so you really don't want to be changing your currencies every decade, right? And the worst case, it should be obvious to everyone that it basically just rolls the dice, and the early adopters of those currencies, perhaps gain more advantage. And then the final other problem, two more, is that it tests the concept of your feature, not the actual implementation, because it's in an altcoin. Now you have to move it into Bitcoin. And then additionally, oh, I forgot. It's not up there. Okay, so let's just move on. Here's, I think we all know what the problems in a soft or hard fork is. The big problem is that, like, people say, well, Bitcoin is like, upgrading the Bitcoin network is like upgrading an airplane in flight, right? But it's not. It's like upgrading the airplane in flight, and all of the passengers are like, members of the Worldwide Wrestling Federation, and they all just are attacking each other on the plane while the upgrade is happening, right? So this is what we're happening today. And then finally, layer 2, it's possible you can layer stuff on top. The biggest problem with layer 2 other than the ones I've put up there, is that anything that works in layer 2 would work better on a upgraded layer 1, right, with the same layer 2 features. All right. So extension blocks are not a new idea, so I just wanted to make sure everyone knew that. So here's the basic idea. You have a Bitcoin block, and somewhere in there you cram a hash, right, of another block, and then through some additional protocol layer or a completely separate protocol, you pass the information about that block. So a few people have talked about extension blocks, but the Achilles heel of them is that in order to have extension blocks, you need to have all the miners agree to start mining them. So what I want to talk about today is an idea I had called FSH extension blocks, are Federated Soft Hard Fork. And the idea is that we can start trialing an extension block at a reduced security model, basically a federated model, and then without changing a line of code, we could move that block to either a soft or hard fork if the block gains economic use, and if it is not full of bugs, et cetera, et cetera. So what are the advantages? Doesn't create a competing altcoin, has permissionless deployment and trial, you're using real money, seamless transition to soft and hard fork, and finally, in my talking with some sort of AppCoin style companies, they actually prefer this idea over a separately mined system. For a company considering like doing a separate blockchain, the question is, do they really have to like maintain hash power? Do they really have to, and then if like the public maintains hash power, there's a certain loss of control. So it may actually be desirable. So here is the idea of a phase 1 federated signed extension block. So what you basically do is you could create a Bitcoin transaction. And what you're going to have, so what we're going to do is we're going to create 2 addresses. One I'll call the ingress address, and one we'll call a holding address. And these are both multi-sig addresses, that are signed by the people who are underwriting, this proposed feature. And obviously, those people would probably be companies or publicly named individuals. So here, the trust model is that you're trusting that the majority of those signers are honest, right? And if not, Bitcoin has grown up, and we're in a world now where we can trial these features and rely on things like the normal legal system, right? If funds are stolen. So basically, this is indicating sort of UTXOs, and individuals will pay to an ingress address, and then a single transaction is made which contains as inputs incoming funds, and then something that I call the continuity address. And what this is basically it's an output from the previous FSH transaction. And so what that simply does is order the blocks, and then on the output side, you might have outgoing payments. So these would be people who are withdrawing money from the extension block system. And then if your incoming funds is greater than the outgoing, then you want to make payments to this holding address. And then your continuity address, which just goes to the next block. And then finally, the extension block pointer. Okay. So I didn't really know what audience I was talking to here, so I think this is probably making a lot of sense to some of you and less sense to others. some of the advantages are that the continuity payment creates a chain of blocks, right? So what you need to do is make sure that, let's say that the signers create one of these FSH transactions, but then it's not committed to the blockchain for some reason. Let's say the fee is too low, right? So now they need to create another block, right? And now both of them get committed to the blockchain. You suddenly have a problem where the FSH block is inconsistent with the blockchain, right? But by creating a sort of continuity address that gets spent on each new transaction, you ensure that only one of those two transactions can be spent to the blockchain. Then finally, in some of the previous extension block protocols, there was an issue where the transaction was not atomic. So, like for example, the extension block address had to be the last transaction in a block, so that it would be consistent with all of the previous spends in that Bitcoin block, right? And so the problem with that is we can't control that because here we're doing this in a permissionless way. So we don't necessarily have the control of any of the miners. So by grouping everything that is needed, so by having the ingress address separate, and then it pays to a holding address, we know that in a single transaction, which both contains all of the the UTX inputs and all the spends and the extension block pointer, it sort of atomically creates a extension block which must be consistent with the money flows in Bitcoin, in your Bitcoin side. Okay, so that's that. So here's some use cases. So what's the advantage of an issuer of one of these federated app coins? So let's say, so I want to go for a moment and say, perhaps you would never actually move out of this phase one if you're like an app coin system. I was, to give an example, I recently had some solar installed on my roof, and so in the US you get these renewable energy credits. Okay, so what basically, if you're like a dirty company and you burn coal, then you have to buy these credits from people who produce solar. So how do they track these renewable energy credits? Well, they have this dial, like an old 70s style dial, that goes around in circles, and I guess someone is going to come into my house and look at the dial once, and then like every quarter I'm going to take a photograph of the dial. Not like I can't, Photoshop that photograph or anything, right? Okay, so this could be a blockchain application, right? So let's imagine that we now, that these renewable energy credits are, this device stores them on a blockchain. So if we used a public blockchain, the problem is, the Ethereum ICO happens, and transactions are blocked for 3 days, right? How's that going to work, right? So when companies look at this sort of thing, they stress out about issues like this, right? I think we heard about yours, and they were recently really worried about, the Litecoin fees, right? I mean, the Bitcoin fees. But switching to Litecoin is just increasing the block size, I think, by a factor of 4. So if Litecoin, overtakes Bitcoin, they could be in the same situation in a few years. God forbid that ever happens. But again, you need to solve that problem, right? I think Dr. Wright's solution is to have absolutely unlimited blocks. And I would love that, but this is a way that maybe we can kind of shard the Bitcoin network into these app coins, because I think some people find unlimited blocks unpalatable. while there's no block space competition, you also don't have to rely on, so what I mean by no reliance on miners is you don't have to sort of generate your own mining capacity. You can just use the Bitcoin mining system. And so it's a public blockchain, though, so there's fewer billing disputes. But the user does have advantages, which is that the issuer can't just, so if you had a private blockchain, the issuer could just rewrite the blocks, right? He could just rewind the blockchain, sign 100 additional blocks, and you'd have a new longest chain, right? By committing extension blocks to the public blockchain, you can be no history rights. You also have Bitcoin moving in and out of your extension block, so then you could easily trade these renewable energy credits for Bitcoin, which makes a lot of sense for people who need money now. And then, oh yeah, so then, so these last 2 points are the idea that although I haven't done the math for scaling, but I do believe, like Dr. Wright, that Bitcoin on-chain could scale for all the economic activity in the world eventually, but could it scale for every single app coin that every single person creates for any silly use? I don't really know about that. So one advantage of sort of these extension blocks is that they are domain specific, right? And finally, like a huge unsolved problem, I think, that's always happened with like your bank statements and e-statements is that you get an e-statement, and when you click on it, it brings you to the bank site and they show you your statement, right? There's no guarantee they haven't changed that statement in the next, you can get a statement from 5 years ago. For all you know, they rewrote the last 5 years of statements. So, again, you can easily turn a blockchain into sort of an e-statement system. Okay, so now let's move on to, so let's say, though, you're not doing this for an app coin. You're doing this to trial features in the Bitcoin network, right? So the next step is to move this system into a soft fork. Now, the way that like SegWit soft fork works is this anyone can spend idea, right? And so although anyone can spend the transaction, the miners enforce that the only spends that are allowed are ones that are consistent with the SegWit extension block. So let me just observe that I can turn this multi-sig transaction into an anyone can spend transaction simply by publishing the private keys, right? Then all of a sudden anyone can spend this, right? And the miners have to enforce it. So we have a protocol here, or a social system, a social set of steps to make this work. First of all, miners agree on a fork activation block, so they could use like BIP9 voting or any other type of coin-based voting protocol. And then in step 2, the miners would begin enforcement, so they would do a soft fork. And what are they enforcing? That this FSH, the FSH ingress address is only spent as input to these FSH transactions that contain a pointer to the FSH blocks. The holding is only spent as input as well, and then the ingress and the holding is consistent with the contents of the extension block. Step 3, and this is something actually that kind of goes beyond the security model for like SegWit, is the signers, before they publish the private keys, could actually test the network to see whether it's actually enforcing the soft fork. So they could post some invalid spends, some bad blocks, right, inconsistent items, and see if the network actually rejects those. And if it doesn't, then we are still assuming that those signers are sort of the benevolent dictators of the extension block, right? So presumably that money's not lost. And finally, when they're satisfied that the network is properly enforcing the soft fork, the signers simply publish the private keys, so then the miners can produce their own extension blocks. So it's quite simple, and as you can see, we moved from a federated model to a soft fork without changing a single line of code. So this is, it really means that your work in the extension block is, well tested when you move it into a soft fork. So step 3 is would be like a hard fork. In this case, whether you could do a hard fork or not depends on the contents of your extension block. So let's assume that it is capable of becoming a blockchain. In other words, it can be mined, it has a nonce, it has proof of work. If that is the case, then miners again choose a new block height, and they simply stop mining the original block and start mining on the extension block as an individual block. So the old blockchain is essentially abandoned. The extension block becomes the the new blockchain. Now, of course, your extension block should really accept legacy Bitcoin transactions and all this stuff, right? So you really do need, your extension block to sort of be fully featured. You could also do a soft hard fork. So basically what you would do in this case is you just enforce, in the soft fork, you create a valid Bitcoin block, but it doesn't contain any transactions other than ones that move money into your extension block, right? So now this looks like, I don't know if you guys are familiar with the soft hard fork concept, but the idea is to use a soft fork to force everyone into a hard fork, right? So what you're doing here is you're reducing the Bitcoin block to basically a header, and it only contains transactions that move money into the extension block, and then all your economic activity occurs on the extension block. All right. So now I want to switch over and ask, how much time do I have? Okay, great. So that's kind of part 1 of this little presentation. Then I thought, okay, so if we have this machinery, let's have some fun and ask, what block should we create? What extension block should we create in Bitcoin Unlimited? So this is not complete. It's a lot of just sort of thoughts that I want to throw out. I don't like to talk about things that that are done for me because it's kind of boring. I like to talk about stuff that I'm working on right now. So here would be your basic Bitcoin Unlimited extension block, identifier inversion. It's got the block height in the header, transaction commitment, UTXO commitment. So transaction commitment, what I mean by that is like the Merkle tree, right, of all the transactions. Block time, difficulty, and then, so this is all about the same, but here's a little thing. So like things like the block height are currently stuck in the Coinbase, right? But just moving stuff around. Pay to the next block. This is something that I want to talk about later. But basically you could, instead of taking all of your, all of the money like as your Coinbase, you could designate some of the fees that you got in the current block and offer it to the subsequent block. And then nonces for mining. So I thought we might as well reconsider what hashing algorithm we're using for a lot of stuff. And so let's just fool around with the fastest one, which is Blake 2. I'm not a cryptographer, so I just need to trust, the PhDs in this subject that Blake 2 is secure cryptographic. So then what would I do for mining? I think that we've proven that, blocks can flash across the worldwide network, and we were moving headers like in a quarter second, but so 1 minute block mining should be perfectly fine. And then so here's so let me switch over to this side and talk about the hashing algorithm and why it would be ASIC boost proof. I don't really think ASIC boost is all that important, really, but you might as well just close out all the people complaining about it. So basically, take the whole block header and hash it, and then add the nonce after that, and then mine it using your normal SHA-256. And so if you do that, you end up with just a single round of like the size of what you're mining is lower than 64 bytes, so it's just one SHA-256 iteration, so you end up blocking ASIC boost. And then, so I want to introduce an issue. I forget if I need to do it in this slide or the next one. Hang on one second. Yeah, okay. So here's a problem. If you're simultaneously mining an extension block and also committing it periodically to a Bitcoin block, the problem is what incentive does a what incentive does the committer have to actually commit the latest block in your extension chain? Why doesn't he just commit the unmined prior block, right? And really, if in a simple way, so it's like it's a similar argument to the argument of the end of Bitcoin, where there's no more Bitcoin fees. So the question is, if you had unlimited blocks, why would anyone ever exchange? Why would anyone ever extend the Bitcoin blockchain? Why wouldn't they just take all of the transactions in the prior block and all the ones in the mempool and create a new block with those, right? And then the next guy, instead of building on top of that, he just takes all of the transactions in that block and all the new ones in the mempool and creates another block, right? So you have the same problem here, which is extension block. The extension block signers might ignore mined extension blocks and just use the next block on the Bitcoin blockchain, skipping all the others. So what I'm going to do is create a economic incentive mechanism to encourage people to include the latest block on the chain. To do that, I want to create a fee pool in the blocks and the ability, as I showed earlier, to pay some transaction fees forward to another block. So what a fee pool is basically the idea that instead of taking all of the transaction fees for yourself, you would put the value in a pool, and then every block that's mined gets a fraction of that pool, say 1/1000th. Of the value that's currently in the pool. So what that does, that actually has two advantages. One of the big ones is right now there's a little sort of hole in the way that Bitcoin works, and that is that a miner could basically create a transaction with a gigantic fee, and then he could pay that. Then when he mines that and not relay the transaction, so when he mines a block, he, of course, reaps 100% of that fee, right? So what that allows you to do is create fees of any size, right? And you don't lose any money. And so this was always a problem with all of the block scalability issues that said we should use fees to determine whether we should increase the block size, right? People would say, well, miners can just create these fake transactions. So if you have a fee pool, though, and you take some percentage of all the fees, you put them in the pool, then a miner who decides to do that loses money. Okay, so fee pools have some advantage beyond what I'm talking about here. So let me go forward and then back. So what we would do here is change the way that fees are paid and use a decay function to determine how much of the fee is paid to the miner of a particular block and how much is paid into the pool. So what I have there is about 10 minutes, and then you can see we never want to pay 100% of the fee to the miner to avoid this this fake fee situation. So 90% if you mine the block, right away, and then that comes down to 0 in 10 minutes. So the idea is that if you're able to mine a block very quickly after the transaction was created, then you reap most of the fees. But if you're not, then the fees go into the fee pool. And by the way, that's not that bad, because you're going to get, if your hash power is 10%, you're going to get that back, right, eventually. But what happens is you don't get a bonus for mining rapidly, right? And the idea is to encourage, the idea of mining of transaction fees, I believe, is to encourage miners to commit transactions to blocks rapidly. So this more accurately reflects this. And what it also does is it would mean that that miners who are mining the blocks in between Bitcoin blocks can basically gain the fees up here. So then they can pay off, say, this much to the next block, right? And so in the end, by producing more blocks, you actually hit the fee curve higher than you would if you created blocks every 10 minutes. So by creating more blocks, you're actually able to give more money to the miner who's mining the FSH transaction block, the block that's connected to the Bitcoin blocks. And now you might say, well, a miner could cheat and change his block time so that he so the block time wouldn't actually be the real time. It would be the one that maximizes, fee payout, right? But that's actually fine, because if you did that, you would have to leave. If you did that, you'd have to leave transactions that occur after your block time unmined. So there's an incentive to move your block time backwards, and that is that you can get nearer to a higher paying transaction. But then there's incentives to move your block time forwards, and that is to include more transactions in your block. So I think I haven't worked out the game theory, but it seems pretty clear that it's not going to affect the system tremendously. So let's talk about a little bit what a transaction would look like. So the first thing that I just talked about is how the fee would be relative to how soon a block was able to put the transaction in the block, right? So because of that, we definitely need a time when the transaction was created, right? Or when it first becomes valid. So Bitcoin today has this idea of end time, where you can create a transaction which won't be valid until a certain number of blocks have passed or a certain time. So we can combine these two concepts. So that's why I call it valid at time. And then it would have, of course, the transaction inputs. And in this case, one thing to consider is, and that's what I've done here, is to just forget about the scripting system, right? Because most of the transactions, I'm not saying remove scripting entirely, because we still have the main chain blocks, right? But most of the transactions don't really use the scripting system, so we can actually save a bunch of bytes by creating a simple multi-sig transaction format where you just specify the number of signatures needed to sign, and then the set of addresses. And then finally, And this is sort of an interesting concept, which I think we can possibly apply to Bitcoin today, is instead of using an out point, we can instead use a, so an out point contains a transaction ID, and I mean, you explained it, right? Transaction ID and an index. But if we replace, so a transaction ID is 32 bytes. If we replace that with instead the block height of the, of the UTXO, and then the transaction ID and the index, then what you're going to end up with is instead of 32 bytes, you end up with maybe 12 bytes. So that actually saves a lot of space, and it has an additional feature, which is that it solves the fraud proof problem, because the transaction is specifically indicating exactly where it is located in the blockchain. So you don't have to search through the entire blockchain for the prior transaction, right? Now, the big disadvantage, though, is that you can't talk about these transactions then until they're committed to the blockchain, right? So this might create some issues for the layer 2 people. But again, this is an extension block, right? It's meant for some sort of specific implementations. And then perhaps you could also allow a standard out point. Now, so that would be what the inputs look like. Outputs, I like the P2SH format. So you could just create an output and then you hash it, right? And you just include that hash. And what's the advantage to that? Is that instead of carrying a whole bunch of addresses through the UTXO set, you just have one 32-byte hash. So it makes your UTXO set a little bit smaller. And then how would you sign these transactions? Well, you would, let's play a little trick with the signing. The first thing is that this TXO triple here, so you could imagine a really directed blockchain reorg, maybe an attack, which would try and replace, it would try and remine a transaction and replace one with a different height. So what you'd want to do is sign all this, and then you also want to include the transaction hash as well in the signature. What you're hashing to make the signature. Do people understand? I better explain this. It's sort of a trick. People realize that you could kind of submarine data inside of a transaction by including it in what's signed, but not include it in the transaction itself, right? And the first use for that was to include the value of the prior input in the signature, right? And so the idea, so the reason why you would want to do that is so that a light wallet, like a hardware wallet, could sign a transaction with these values, right? And it doesn't have to check the blockchain to make sure that the previous input values are real, because if they were incorrect, then the signature would fail. So we'll do that for two things. We'll both we'll add both the transaction hash and also the input value, and then you just sign that hash, and then the transaction hash would just be the hash of the outputs and the inputs. So this signing and hashing scheme would solve transaction malleability and the quadratic signature hash problem. Oh, here, I jumped ahead, I guess. So I did a little bit of calculating, and so if you use that, some of those tricks I was talking about, then if you create a standard transaction with one input and two outputs, you get 157 bytes. The current Bitcoin uses 226 bytes, right? And just let me observe, in Bitcoin today, what if you use this trick? Instead of storing the outpoint as transaction ID and index, what if you actually, in all cases where you could possibly store it to the database, what if you stored it and sent it to each other as you know, block index transaction ID? I think you would save this exact same amount. And the sort of the detriment would be that you'd have to look up these transactions in the blockchain, but you have the blockchain because you're a full node. So I think that could save us a lot of money in, I mean, a lot of space in the blockchain right now. Of course, our problem is not the size of the blockchain, although some people like to argue that, because as Dr. Wright was saying, you know, hard drives are so cheap these days. Okay, so I've written a lot of this, and I have, you know, these extension blocks being created, and you know, in reg tests and test nets and things like that. But I did it in Python because I want to just create a reference implementation that's simple to read. And so this is, you know, where you can go to look at my stuff. It's obviously a work in progress. One thing that I haven't done is done the P2P, you know, protocol layer. And that's it.
Questions, anyone? All right.
Yeah, I have a question with regards to this soft fork as you know, in an extension block as an upgrade mechanism. So how do you then deprecate the old soft fork? Is it really only used as test bed and then just thrown away? Or you don't get the data back from those initial soft fork, or do you just maintain it, or do you deprecate it? How do you do that?
In the soft fork case?
Yeah, for instance, when you say, okay, we do a SegWit in an extension block, and then if we like it, we move it back to the main chain. What happens with the original extension block?
Right. So in this case, you would never move it back to the main chain, right? The act of adopting it in Bitcoin would be that miners start to mine and handle both the extension block and the main chain block at the same time.
So you would not be able to deprecate the extension block then after moving it back?
No, it would be more like deprecate the main chain block. If your extension block is, you know, and that gets you into the soft hard fork and hard fork situation.
Okay. All right. Should we go for this? Oh no, not you. The throw. I was just, you're good.
Hi. I saw your proposal about the fee pool. I actually did a few calculations myself with this more simplified version of that. And my conclusion was that the security lowered from 51% to 38.2%. I'm just curious if you did any calculations regarding how secure that fee pool system is.
Why would you think that the fee pool would lower the security?
Well, you can have a big miner that mines a lot of blocks after each other. I just learn about your proposal. That's why I'm asking. How secure is... If you have a big miner that mines a few blocks in a row, then he can publish a chain that he stealth mined while others are mining the main chain. That's why I'm asking. Just a question. Really? I'm curious.
No, I know. I'm just thinking about it. It would seem to me like... I mean, I haven't like considered that. It would seem to me intuitively that since the large miner is giving fees away to future, you know, miners, that it would actually be worse for him to do that, not better. I would like to, you know, see your reasoning on that.
All right, anybody else? Oh. Great. There you go.
Thank you. You were talking about the one input and two outputs for 157. Can you give more information about this one?
Right. So what I mean is, how many bytes does a transaction consume, right? So in Bitcoin, if you have one input and two outputs, and why would you have one input and two outputs? It's because you're spending money, one of your UTXOs to someone else, and then you have change, right? So that's a very typical Bitcoin transaction, and so. Bitcoin uses 226 bytes to do that approximately. I just got that from looking at in Bitcoin QT. If you write in a transaction, it tells you how many bytes before it tells you how painful the fee is going to be. And then if you do the same calculation, the thing is that by using this TXO triple as your inputs, you're saving a lot of bytes, right? So that's what you end up saving. There's actually another trick that we could do, which I'm contemplating, and that is if someone ever reuses an output to address, instead of actually specifying the output address, you could specify a TXO triple of a prior moment when that address was used. I didn't really think that was probably worth the effort, though. Next question.
Who had a question? Someone else had a question back here? See anybody else?
So I'd like to just say one more thing about this, which is that, and about Bitcoin in general, which is that we're entering a time of I think a lot of uncertainty with SegWit 2x and possible hard forks and UASF, right? I think a lot of this uncertainty is because we don't know how to upgrade Bitcoin, right? I think both sides of the blockchain debate has pointed to the other side and said, your code is untested. I think that's in the main somewhat true on both sides. And a system like this, even though it requires trust, it only requires trust for people who want to test out the system, right? And they're trusting the signers. So I see a system like this working no matter what chain, fork, soft fork ultimately wins. And whichever one wins, we're just going to have this exact same problem a few years down the road. And a system like this can allow us to perhaps resolve the problem a little bit better next time.
All right. Great. So I'm just going to ask, I've got this. Again, most of this is way over my head, but so you could be testing, in theory, multiple solutions to scaling at the same time and just see what works.
Absolutely, yeah. And of course, the qualification is that your security model in the extension block is lower because you're trusting individuals who are signing Bitcoin, a multi-sig account, and they're basically holding the Bitcoins on the extension block, for you, right? So if those people are compromised, then the extension block is compromised. However, I actually think that's almost an advantage because, as Dr. Wright was saying, we want the miners to take over these systems so that we end up with a really hard security model and a lot of fees going to miners. The only way to do that, though, so if the extension block was perfect, that would never happen, right? But the fact that the extension block does have a weaker security model would encourage miners to adopt an extension block like this so that it would gain a higher security model.
All right. Thanks, Andrew. And thanks also as one of the primary sponsors of the event, and again for some people from Bitcoin Unlimited helping prepare yesterday.